So after the transition fit, we will continue. Now this is a nice example. Okay, so like a particular assembly is given here, and we have to think of it is a thinking exercise. What kind of the fit is required between these parts? Like here, number A is shaft which is rotating in the bush. This is a shaft and this is a bush, so this shaft is freely rotating in the bush. So what type of the fit it should have? Clearance fit, interference fit, transition fit? Definitely not interference fit. It should be clearance, so that it can freely rotate there, right? It should have smaller diameter, a slightly smaller diameter. It should not be very tight fit. It should not be tight on the bush and forcing the bush to rotate. No, this is just the bush bearing, okay, not the ball bearing. So it should be either an interference fit basically. Now this is B, part B. This is a bush fixed in the housing. This is a housing and the bush is fixed into the housing. So here definitely the bush outer diameter should be more than the whole diameter in the housing, so that the bush is fixed there. It should not rotate. It should have the interference fit there in the housing. So house interference fit there. So we should control the size of the bush and the size of the hole in the housing, so that you always get interference fit in that case. Number C here, as you can see, it is a bush and it is secured on to the gear. So this looks like a gear, this and this looks like a gear, and in that the bush is fixed. So definitely it should again have interference fit while it is fixed, secured into the gear. Then D is the base plate of the gear unit, and which is secured on the casting by cylindrical pin. The base plate of the gear unit, this is a base plate of the gear unit, which is secured on the casting by cylindrical pin. Okay, so it can be interference fit. You push fit into that. E is, say, gear with a bush rotating on to the pin. This is a gear with a bush. So this needs like some practical understanding of the part, how it is working. Okay, so gear with the bush rotating onto the pin. So now this is rotating onto the pin. So this is allowed to rotate. So it should have the clearance fit, right? The pin should have smaller diameter than the bush internal diameter, so that it is rotating there inside. Okay, G. Okay, F is somewhere. F. This is F here. Okay, F with the pin is secured onto the base plate. So this is a base plate and pin is secured on the base plate. Secured means interference fit. It is tight fit here. It is a hold here in place, but here it is allowed to freely rotate on the bush. Okay, so here it is interference fit. Here between the bush and the pin, clearance fit. In the bush, the pin and the housing or the base plate is the interference fit. So depending on the application, you should have the bush fit, the clearance fit, interference fit, transition fit. G is a bush with a plate. There is a G now. This is a G here to here. So this is secured inside. So bush with a plate. So it is just to hold it down. Now these tables which we were talking about, okay, or the system of the tolerance grade, especially the whole letter symbol method, where we use the letters to represent a specific value for the tolerance. Okay, the whole picture is clear once you understand everything. Okay, step by step, maybe sometimes a few concepts are difficult to understand. Even sometimes I feel like, I should tell this to the student first or this to the student first, and I'm not sure about that, right? So because to understand this you should know this, and to understand this you should know. So basically these things go together. Even if I tell this first or that first, will not help. So fine, what I mean is there are two bases or two ways of establishing those tables. So what table we are talking about? we have discussed these tables here. These are the tables I'm talking about. So these tables are giving us some tolerance value. So here we have to calculate the numbers, right? Another form of the table is, okay, sorry, this is another form of this similar table is here, the same table, okay, same table. So what the table is telling here is H11 C11 for 0 to 3 use this tolerance value, 3 to 6 use this tolerance value, like this, and there are tables available. So this particular table is ISO table. This is a whole basis system table. I can't zoom in, I think, in this one. Can I zoom in? Okay, you can see here. Now this table, if you see, it is written here at the top, clearance fit. Okay, now if you see here, this is tolerance value, this is a tolerance value on the hole, and this is a tolerance value on the shaft. The hole is the shaded area, shaft is, because it is a lowercase letter, white area. These are the shaft tolerances. And if you see both together, this is plus plus, this is minus minus. What is the meaning of this? This means the hole is big and the shaft is small, so that is giving us a clearance fit. So here if you see, look at the hole, the minimum or the lower size for the hole is 0, lower number for the hole is, upper number is something, because you drill the hole by drilling tool. So the hole diameter cannot be less than the drill diameter. It can be few microns more depending on the type of the reamers or the broach if you are using, or how much time. If you drill it and just stay there, okay, fine. Or you drill it and just keep there drilling to clean all the last pieces of chips and the burrs, it will remove little more material and it will be few microns larger. Okay, but in any case the drill size cannot be less than the the hole size cannot be less than the size of the drill which you are using. So that's why here the lower number is 0, upper number is by few microns. This is for the hole. Shaft is minus minus, and from the basic size you are reducing the shaft less and minus minus. So that's why the shaft can enter into the hole, giving you the clearance fit. Now if you go on this side of the table, here it is interference fit. If you see here, the hole is like, okay, let's see some hole here, this hole, the plus tolerance, and this is for the 80 millimeter to 100 millimeter diameter. Okay, so plus value for the hole is 35 microns, less is not possible obviously. And the shaft here you are making plus value, plus 37 or plus 59, and you are making sure that the shaft is larger than the hole, so that will give you the interference fit. So this table is based on the hole basis system. Basically, if you always see here, the hole value, lower number is 0 0, upper number is something. All these cases, even clearance fit, in between for the transition fit to interference fit. So the hole basis, any hole value, lower number is 0 always. All these numbers for the hole in this table, if you see, the lower number is 0 for the hole. And for the shaft, the number here is minus, and very big minus number. And if you go here, it is reducing, as you can see, and here it is going plus. So now the shaft value is varying. So if you want clearance fit, the shaft is minus. If you want interference fit, shaft is plus. So this is the hole basis system. So hole basis system is a system in which you can say we decide the tolerances on the hole first. I am not saying we make the hole first, okay? You can make anything first, but we decide the tolerances on the hole first in that table. In that table of the hole basis system, they decide the tolerances of the hole first, and then they vary the tolerances on the shaft. Make it minus if you want clearance fit. Make the shafts larger if you want interference fit. So this is more widely used. Also, the hole basis system is preferred. It is preferred system in most cases. Why? Because generally the holes are, the best way to make the hole is using the drills and the reamers and the broaches, right? So these are the standard tools which we get for drilling the holes. So you don't have much control on the hole. You know, you can get the steps, 10 diameter drill, 12 diameter drill, 14 diameter drill, and so on. Similarly, the broaches and the reamers are in the steps only available. These are the standard tools for drilling. This is the most economical way of drilling. so you get in the step, so you don't have much control, so you get 12. So you decide the diameter of the hole first, and then shaft generally is made by the turning operation. There is no limit in the turning, external turning operation. You can make shaft of any random size, but to drill a hole of say 11.735, you will not find a drill of that size, right? You will either maybe find 10 or 12, maybe sometimes 11 also, but basically these are the standard tools available for drilling. So turning, you can get any number for turning. So that's why the hole basis system is more commonly used. Okay, see, there is another way of drilling the hole, which is you drill the hole and then you do the internal turning. So then you can change the hole diameter, internal diameter to any number. That's possible, it is not impossible, but generally it is not a preferred way because it is not economical way of doing it. And also it cannot be applied, that internal turning cannot be applied for the small diameter holes, right? It cannot be done. Small diameter holes only drill, any small drills only drill. You cannot do internal turning because there is no space for the tool to go inside, and when especially you are working with the metal, at least some strength size is necessary for the tool. So that's why the hole basis system table is more used. So there is a table available for the hole basis system, which will give you the required type of the fit, as we have seen that table. Also there will be table for the shaft basis system. This is shaft basis system. So some places, like in the textile machinery, the shaft is a permanent big piece, and there are thread gauge like this, these are the thread guides. These are guiding the threads to make the cloth for the in the textile industry or some kind of the special applications. So we can see the shaft is very predominant, and these thread guides, because the thread is passing through them, will wear out after a while. Maybe every year you have to change the thread guide. It will wear out, you have to change it, wear out, change it, because generally they are made by ceramic or sometimes metal, and while the thread is passing, large heat is generated, and it is always a friction there, while the thread is passing on the machine looms. We're talking about the textile here. So you have to change this part only, you don't have to change shaft every time. And some of the thread guides maybe are rotating like a roller, and some of them are maybe fixed to give the direction to the thread. So some may be clearance, some may be interference. So in this case the shaft size is decided first, and depending on the requirement, maybe you need sometimes clearance or maybe interference fit, you can have the size of the hole later on. Okay, so in that case you use the shaft basis system. Okay, so but again the hole basis system is more preferred because the holes are we use like in standard tools like a drills, reamer, broaches. Okay, that's why this is more commonly used. This is only used where the shaft in a specific application is always there, and you have to keep changing the other parts on the shaft on the basis of the shaft size. So you will have the shaft basis system also. So the table which we have seen, that is the hole basis system table. Okay, like this many tables are available. So this table which we have seen is similar to the tables which we have earlier seen. Here directly the tolerances are given, there also tolerances are given, but only the way of presentation is different. It is the same thing, same steps, same numbers, and there are more numbers, more letters, right? We have only few letters there, like CH11, H11 combination. There are few combinations, like maybe you can go and look at it again, few combinations here, H, but there are letters from A to Z, so more pages for the table will be available and needed. So this is just a sample for us to understand the concept. So we have seen that what is a hole basis system and what is a shaft basis system, and also sometimes it is very important to understand why the hole basis system is more commonly used. Now again this is the same thing, example of the hole basis system, more explanation. Now what happens here in the graphical representation? Okay, this is a basic size, this is hole basis system, this is shaft basis system. Okay, this is shaft basis system, this is hole basis system, shaft basis. So this is the shaft, so this is a basic size, all shafts basic size. Okay, starting from the basic size, it is based, and now we change the size of the hole. Hole is big, so giving you more gap. If you make hole here in this range, then you are getting the transition fit, it is less also, more also, and here it is interference, and more of the interference. So hole is inside the shaft, too much interference. If you see here, this is a hole basis system, so this line, this is a hole. So this is basic size of the hole, This is minimum limit, maximum limit. I said always the lower number in this case is 0. So hole is not getting less than 0. In this case it cannot be less than the basic size because you are using a particular size of the drill. So always hole is minimum that size, basic size. Minimum is basic size. Maximum can be whatever maximum limit of the hole. Okay, it can vary, no problem. Now you have the shaft. This is variation in the shaft, minimum limit of the shaft, maximum limit of the shaft. So in any case the shaft is smaller than the hole, so it is a clearance fit. Here it is a transition fit. If it is going up here, you can see the transition, and here it is complete clearance. Okay, and the combination of the letters they are telling, they are suggesting, okay, use S7 N5 hole basis system if you are using for the same. Yani this is the table suggested for, this is very important to understand, and not very important for you to understand, but a very interesting fact here. This table is equivalent fit on the hole basis and the shaft basis system. So if you use for the same type of the interference or same type of the interference in the hole basis system or in the shaft basis system, you have the equivalency. If you want clearance, maybe in the hole basis system they say use this combination. If you are having the shaft basis system, use this combination. This is equal. If you want say more clearance, here maybe this one. This is less clearance, this is more clearance maybe. Now here if you go, because we have to see the actual numbers for that to the basic size, we will also see them. Now for the interference fit, maybe if you are using the hole basis, this is one example. If you want equal amount of the interference, same amount of the interference, not too much or less interference, and you want to use the shaft basis system, you can go this letter combination, this letter number combination, or this letter number combination. So what is this one? How to get the number for this one, like H6 or N5 or N6 or H5, there will be tables like this available, like this. Now this table doesn't have all the letters and the numbers, as this is just the sample table. So H7 F7, this is one combination. Here this is one combination. H7 G6, this is another combination. H7 H6. So the capital letter, small case letter, this is a combination available. Then you use a particular recommended combination. For that, tolerance values are provided in the table, and depending on your basic size, you can go choose your tolerance value. We'll solve one example for that also. So that is about the hole basis and the shaft basis system. Now generally we said we want a random assembly for the assembly line production, and you should be able to randomly interchange part, right? Parts should be interchangeable, and that should be randomly. But if you want more closer control, like for the pistons and the cylinders of the engine, like some parts where the critical, it is very critical. Suppose you are looking for the clearance fit, it is very critical that you want to have very minimum clearance between the two. But you know, we have calculated in the clearance fit, there is a maximum clearance, there is a minimum clearance, but you want the minimum clearance only always. So how to achieve minimum clearance in that case? Suppose it is a gap between the two parts and you want the two parts to fit as with less gap as possible. So there is a one way of doing it. What you do, as I said, you have a shafts and you have the holes. Suppose 100 shafts and 100 holes. So what you do, you take the shaft, you may inspect it. This is selective, this is not random. Randomly you choose and assemble, still always you will get the clearance fit. But you want to have that clearance to be very small. So in that case, you can group the parts. Like you have 100 shafts, so make 3 groups of the parts. You know, these shafts in one box 100. Okay, so you make 3 groups of this from one box. Okay, you make some with near the larger maximum limit shafts one place, near the minimum limit shafts another place, and in between another place. I'm just making 3 groups for easy. Okay, maybe you can make more groups, but you can see what will be the effect. Similarly, from the holes you say the same thing. Maximum limit hole you make in from that box, you keep it in another small box. Smaller limit holes you put into another. All are within the limit. Okay, but in that, near the small minimum limit, near the maximum limit, and near the middle, you are making 3 groups. Now big one you assemble with the big one, and small one you assemble with the small one. So you try to maintain always the minimum possible clearance. What is happening here? In case of the random assembly, you just put it. Sometimes the clearance is very less, sometimes it is maximum. That is varying. But you want more quality control without spending more time in the manufacturing. because in the manufacturing also it is possible by closing the tolerances, but then you have to use more sophisticated machines, so that will be expensive. Here what you are doing, instead of that you are slowing down your production rate, because instead of directly randomly assembling, first you are grouping them, measuring them, making into the group, and then you are assembling them. It is slowing down the process, but without spending more on the machining, you are still trying to achieve the minimum clearance there, any minimum gap between the parts. So this also is sometimes done. Now here, as we discussed before, for a particular type of the application, they are recommending like use this letter combination or use this letter combination for these applications, and like this information is available in the design books, in the handbooks available for that particular type of the application. Use this type of fit, for the another application use that type of the fit, and so on. Okay, you can see there are many types here. If you even see the clearance fit, it is not just one clearance fit. Precision sliding fit. If you start from the bottom, slide running fit, loose running fit, easy running fit, normal running fit, close running fit, precision sliding fit, any how much is the gap between the two is varying, and depending on the application you can use a particular letter number combination. What you mean by using a particular letter and the number combination, we will see here. Okay, now I said we will use this table to find a particular number. Okay, now what is the example here? If you are having the pen and pencil, you can write it down also. Okay, we want to calculate here for the given hole and the shaft system. The basic size is 10 millimeters and the tolerance value is 7P6. So we have to find out for this basic size of 10 millimeter, we have to find out, I hope I am in the 10 millimeters. Okay, because I am not sure if I am using, I think I feel I used 18 millimeter in the example, but let us see. So it's 7P6. So we have to find out what is the exact maximum limit and the minimum limit of the hole. When we say find out the hole size means maximum limit, minimum limit for the hole with the tolerance. We want to find the tolerance with the size with the tolerances, right? Shaft size, and we have to also find whether it is a clearance fit or the interference fit. Fine. Now the hole tolerance is H11. Hole tolerance is H11. We know capital letter for, I think I am messing up here something. Okay, let me change these numbers here. This is 18, 18, and H7 P7 I am using, or I am using H11 C11. Okay, I am using another number in this example, and the basic size is 18. Okay, fine, because I made many examples. Okay, so 18 is a basic size and the tolerance value is H11 C11. So I can ask you the same thing. This is a good example for you also, like in the quiz, if I ask you this question, or in the assignment if I ask you the question, I will change this basic size, I will change the tolerance value, and I will ask you to find out what is the hole size, what is the shaft size, and also the third question, not 2, 3, the third question here, to identify the type of the fit, you know, whether it is a clearance fit or the interference fit, how we go about it. So the hole tolerance is H11. So uppercase letter, why we say it? Because uppercase letter is for the hole tolerance. Now from the table, we have this table. Okay, I'm just taking the zoom in view of the table here. We go for the H11. This is H11. We go for the H11, and the basic size is 18. So I should be here 10 to 18 in this row. I should be in this row. Okay, 10 to 18 in this row and in this column, H11 column, and in the row 18. Don't go here. Don't go the next, because this 18 number is here also and 18 number is here also. This is over 2. If the basic size or the nominal size is 10 millimeters, more than 10 millimeters to 18 millimeters, then use this one. If it is over 18, yani 18.1, you go to the next row. Just for 18 you should be here. Over and 2, this is the meaning. Up to 18 you should be here. Over 18 you go here. So we are not over 18, we are up to 18. Okay, so in this row and in this column, this number here is our tolerance value. But remember, this is in the millimeters and the tolerances are in the microns. Okay, this number is for the tolerance, and this upper value of the tolerance, this lower value of the tolerance on the whole. Okay, so this is giving us a tolerance value 1, 1, 0 and 0. This is our tolerance value. So the whole tolerance value is 110 micron upper value and 0 micron is a lower value. So I have to convert it to the millimeter. So this is 0.110 millimeters, and 0 millimeters is a lower value of the tolerance on the hole. So I want to calculate the hole size, maximum limit and the minimum limit. What is the maximum limit? The basic size plus upper value. That is the maximum limit on the hole. Basic size plus upper value, that is giving us the maximum limit on the hole, which is, you can calculate. This is add just together, fine. So this is your answer, first answer. Okay, maximum limit on the hole. What is the minimum limit on the hole? The basic size plus another number. If it is a plus, just add. If it is a minus, subtract. Okay, just, you don't have to do anything. You can use the plus sign only. Okay, if it is minus, then you will subtract. If it is plus, as it is. So for 0 doesn't matter. So minimum limit 18 plus 0 or minus 0, whatever, 18 millimeters. So you've calculated the hole size. Now let us see if I am calculating the shaft size or no. Yeah, it is correct here. Now the shaft tolerance is C11. Okay, because lowercase letter. From the table, from this table, we use C11. So here we should find the shaft tolerance value, and here in this place, in the C11 column, and 10 to 18, because 18 is a basic size, we find the tolerances on the shaft. These are the shaft tolerances. These are in the microns. Okay, so this tolerance minus 95 microns and minus 205 micron is a lower value of the tolerance. So if I convert it into the millimeter, because I want to add it to here, so if I want to add, they should be in the same unit, right? So this is minus 0.095 millimeters, and minus, keep the sign as it is, as in the table, minus 205. So the maximum limit on the shaft 18 upper number. Maximum is 18 upper number. Upper number is minus, so you have to subtract. So this is maximum limit still for the shaft. You can calculate and you will get this number. For the minimum limit 18 and the lower number. It is minus, so use minus. It is minus, use minus. If it is plus, add it to the basic size. Okay. So this is the minimum limit on the shaft. Now you can see that the shaft is smaller than the hole. Shaft is smaller than the hole. So what is the type of the fit? What is the type of the fit? It is clearance fit, right? It is a clearance fit. So we identified the fit, and actually from the table itself is clear, right? So that's it. So I give you